Alright, welcome back to Physics 11. So this is going to be the first video of the new unit on work, energy, and power. So hopefully you remember some of this stuff from grade 10 where you learn about work and energy. And let's take a look at energy. So energy is the ability to do work. So basically work and energy can be used interchangeably. Now both of these are scalar values and they use the same units of newtons times meter or Newton meter or joules. So again, these are derived units. So you can use either, again, joules, capital J, or Newton time meter. So work has different meanings in everyday language. In physics and in science, we define it as either change in energy, so final energy minus the initial energy, it's going to be work, or the product of a force and distance. So the first definition is something you often see in thermodynamics, so you might see this in your chemistry unit. And the second definition is basically whenever you're dealing with vector forces. So notice here that we don't have arrows on top of F or D, even though when you talk about force and distance, or displacement rather, those are vectors. So the proper or the full definition, I should say, if you look in your textbook, is written as the work equal to the absolute value of the force, right? So that's why we don't include the arrow here because basically we just drop the arrow, which means this is the magnitude only. And same thing with the distance. We drop the arrow because that's the magnitude only. But again, the proper definition or the full definition looks like this. We have the absolute value of the force vector. So again, the magnitude of whatever the force is, cosine theta times the magnitude of the displacement. So this is the full definition that you're going to see in Physics 12 and later in university. And the reason you didn't see this in grade 10 is because cos theta was always equal to 1 in grade 10. So the reason it was equal to 1 because you always had your distance and your force in the same direction, right? Both those vectors in the same direction, which means that theta here equal to 0. So if you take the cos of 0, you will get 1. That's why it just goes away. But in Physics 11, we do have some cases when we have to deal with 2 dimensions. So you may have a case like this, and definitely more so in Physics 12, we have the force applied in a different direction as the displacement vector. So that's why I end up with this angle theta, which is again the angle between the force vector and the displacement vector. So the full definition is the one that you want to use whenever we have 2 dimensions. So we'll see a couple of examples where we have to use this definition and not the definition from grade 10. So let's take a look at a case where we talk about work being done on something. So let's say if I hold 30 kilogram weight at a height of 1.5 meter, I'm using energy, therefore I'm doing work. But the work not being done on the weight, it's been done on my muscles. So I'm using energy in my muscles to hold out that weight. So you can also think of it this way. Though I am exerting force on the weight to hold it up, the distance traveled is 0. So the object, the weight hasn't moved. So therefore there is no work done on it. Okay? Now, how would you calculate the amount of work that's been done on this weight? So here's our example here. And again, it says here, if I lift it up from the ground, right, I had to counteract the force of gravity. So the force applied here is going to be equal to the force of gravity. So whenever you deal with questions, whenever you have to lift something from the ground against gravity, we're going to have the following definition for work. So again, when an object is lifted against gravity, the formula becomes W equals mg times h. The mg comes from force of gravity, so we can extend this here. So Fg, like that. And of course, Fg, we know that equals to m times g. So we end up with, replace d with the height, we end up with mgh. And if you think of the definition of potential energy from grade 10, you can actually derive it from this case here. So whenever you're moving something against gravity, you're actually looking at the potential energy of the object, which is mgh. So in this case, in our example here, if you have a 30 kilogram weight, so perhaps weight wasn't the best word to use here, let's say object, we plug in the mass, which is 30 kilograms, times the gravity, or acceleration due to gravity, 9.8, times the height, which in this case is 1.5 meters, we can get our work done on this weight to lift it, which in this case turns out to be 440 joules. So again, 2 sig figs in the final answer because 1.5 has 2 sig figs. All right, so here again are the definitions for all the variables. So let's take a look at 4 different examples. Each example deals with slightly different force. So this first case, it says a 10 kilogram pumpkin is moved horizontally 5 meters at a constant velocity across a level floor using a horizontal force of 3 newtons. How much work is done in moving the pumpkin? Now, one thing to keep in mind, whenever you're trying to find the work, you're only going to use the force, one force at a time. We're never going to use the F net, okay? So in this case, if you have your pumpkin, we have normal force acting on it, we have gravity acting on it, we have our force applied here, and we have our force of friction, which will act in the opposite direction to the force applied. But again, how much work is done moving the pumpkin? The only force involved in moving the pumpkin is going to be the force applied. So when you're looking for the work done, you have to use the applied force, not the F net. So in this case, our work is going to equal to the Fa times the distance. So we get 3 newtons times 5 meters equal to 15 joules of work. So again, the message from this is that the applied force is the one we need to use in order to find the work done. Again, not the net force. In some cases, we have to use the F net to find the force that we're interested in finding the work that's been done by that force. But in some cases, you may not need to use the F net equation to find the force because like in here, it's already given to you. So here's a second example. It's kind of similar to the first case where we were talking about the weight being lifted. So we have a 3 kilogram pineapple that's held 1.2 meters above the floor for 15 seconds. So we're not lifting, we're just holding it already at that height. So how much work is done on the pineapple? So if you're not lifting it, if you're just holding it at a certain height and you're interested in how much work you're doing, okay, even though your muscles are applying a force, the object is not moving up or down. You hold it constant at 1.2 meters, which means the distance traveled here is going to be 0. So if the distance traveled is 0, you will end up with 0 work done. So the work equal to the force times distance. So if this is 0, that means that no matter what the force is, if you plug in 0, anything times 0 is still going to be 0. So the amount of work done is going to be 0 joules. So you can hold it for 15 seconds, you hold it for 2 hours. If you don't move up or down, the work done is 0. So the message here is that if there is no distance, means there is no work done. Okay. Now this third example, we will use the work equal to F times cos theta d. So again, these are scalar, they're not vectors. So we have 50 kilogram banana box is pulled 11 meters along a level surface by a rope. If the rope makes an angle with the floor of 35 degrees, and the tension of the rope is 90 newtons, how much work is done on the box. So this is going to be our force applied, okay? And again, this is not parallel to the ground anymore. This is going to be at an angle of 35 degrees. So let's draw our free body diagram to figure out what's going on here. So we have our normal force, our force of gravity, then we have our applied force, let's call it F, and we have friction force. Now in this case, the angle is going to be, again, between the horizontal and the force applied, F. So we only interested in the x component of this vector because that's the only component of the force that's actually going to move the box. The y component is not going to do anything. So we only care about the component in the x direction. So let's break this force vector into components. And again, this is nothing new here. We've done review on vectors at the beginning. So we know that we need to use some trigonometry here to describe it. So we have our Fy and Fx. And this is our F, which is given to us, 90 newtons. And this is going to be 35 degrees here. So we are interested in Fx. You're given the force applied 90 newtons. So that's going to be the hypotenuse. This is the adjacent side. So adjacent and hypotenuse, we have to use cosine. So remember the trig. We're going to write cos theta equal adjacent over the hypotenuse. So in this case, the adjacent is the Fx. And the hypotenuse is the F. So now we can replace it with numbers. So we're going to write cos of 35 degrees equal to Fx over 90.0. So you're going to solve this for Fx by cross multiplication, and you get your value for the applied force along the x-axis, which is 90 times cosine 35. So that's where that cos theta comes from, is because you're interested only in part of the force, so you're interested in the x component, so we have to use this instead of just the force applied, because again, it's not in the same direction as the motion. So when you find the work, we're going to use just the part along the x-axis of this force times the distance traveled. So Fx is all of this, so I'm going to plug it in as is, cos 35, times the distance, which is 11 meters. So once you multiply all of this, you will get a a work of 811 joules. Okay. So again, the message from this example is that we only use the component of the force that's in the same direction as the displacement. Right? So if you pull along the x-axis, you want to use your Fa along the x direction. For example, if you're lifting it, then you would use your Fy. So again, use only the component of the force that is in the direction of motion. So here's the last example. And this example covers pretty much everything we learned. It will cover some kinematics, dynamics, and work and energy. So we have a car that's traveling 61 kilometers an hour. It's brought to a stop while skidding for 42 meters. What is the work done on the car by frictional forces? So first of all, whenever you're dealing with kilometers per hour, you have to convert it to meters per second. So I already did this, so you don't have to do that step. But again, remember, you have to have meters per second. So this equals to 16.94 meters per second. So here's our free body diagram. We have our normal force, force of gravity. Now, once the engine is, let's say, not working when you're braking, well, the engine keeps working but disengages, the only force that's acting in the car is the force of friction that's slowing it down. So those are going to be the only forces acting on this, and we only care about the x direction here. So basically, we need to find force of friction, because the question says, what is the work done by the frictional forces? But in order to find that, we need to find our acceleration, and then we can have our F net equation from which we can find our force of friction. So in order to find the acceleration, we have to use kinematics. So let's list what we know. We know that the car has to come to a stop, so the final velocity will be 0 meters per second. We know the initial velocity is 16.94 meters per second, so that's our V naught. We know the distance is 42 meters, and the acceleration is the unknown. So there's an equation that you can use to find the acceleration without time, and that's going to be the acceleration given by the change in v squared minus v naught squared over 2d. So if you plug in the values for this, we get 0 squared minus 16.94 squared over 2 times 42. And the acceleration in this case turns out to be negative 3.42. Okay, so we know that the reason the acceleration is negative because the car is slowing down, so it's acting in the opposite direction of motion, so that's why it's negative. So now that we know the acceleration, we can come up with the F net equations. Now we're going to use dynamics. So we use kinematics first. We found the acceleration. Let's write the equation, the F net equation, to find the force of friction. So I'm going to make force of friction positive here, so I don't have to do an extra step in rewriting it. So we'll make this positive. And again, there's no other forces, so this is going to equal to our MA here. So force of friction is going to equal to the mass, which is 1385, times the acceleration, negative 3.42. And this equals to negative force of 4,737 joules. Newtons. This is a force. So now that we know the force of friction, we can now find the work done by frictional forces. So our work equation is going to be force of friction times the distance. And I dropped my negative. So that should be negative there. So in this case, we get negative 4737 times 42 equal to negative 2.0 times 10 to the 5th joules. Now the reason we get negative work here is because if you think about it, change in energy, we have a certain amount of energy at the beginning while the car was still going at 61 kilometers an hour, and then zero energy at the end. So we have final energy is 0, initial energy is a certain amount. So let's wind up with negative work. So you can have negative work because our change in energy ends up being negative. So that's the message from this example, is that since our work is a change in energy, work can also be negative. It doesn't always have to be positive. So let's wind up with negative work in this example. All right, so that's all for now. Make sure you do the practice questions, and on the worksheet 7.1, there's a couple of questions I believe you have to use 2 dimensions, so you have to use the cos theta there. So question 5 and 8. I'm not sure about 8. It might not be. But anyway, if you have any questions about any of those 10 questions, make sure you post them in the comments below this video on Teams.